ionization try to understand what enthalpy, energy, potential, IE. Ionization enthalpy, we have to first understand the definitions. So the ionization enthalpy is the amount of energy required to remove an electron from the outermost, or remove a loosely bound electron from the outermost shell of a isolated gaseous atom. Let's move from one point to the next. It is energy required. So what's the process that requires energy? Is it endo or exothermic? Courtney says endothermic. I think she's wrong. Who is with me? Everyone is with Courtney? Sure? Okay. So it's the amount of energy required to remove an electron. Okay, so you have to remove. But you have to remove from, so let's assume you have sodium and you are removing an electron. So what is sodium becoming? Na plus, right? You're removing an electron. The energy is released and we call it delta H negative. Who has not heard about this term, delta H? It might, many of you. Have you heard? You have heard, okay. Tiffany? Any idea? Can anyone explain why this is negative? When I say the energy is released and I say it has to be delta H negative, why? Why does it have to be negative?
Because you're starting and you're releasing, so it's decreasing.
Yes. So, you had some energy. So this is energy, this is the reaction. So you had some energy, and now, so this is the reactant. And when you are becoming a product, somewhere here, when you are becoming a product, so you had some energy, E1, and now you have, or ER, E of the reactant, and now you have some energy, E of the product. When the definition of delta H means delta means change. That's delta of anything means change. And what is change? Final minus the initial. It's always final minus initial. So this is final minus initial. So what does delta H means? Delta H means, delta H of the reaction will mean delta H of what? Reactant or product? Product minus of the reactant. Now, based on this and that, can you say what is going to be the delta H of this reaction? So, ER, let's assume this is negative 10, and this went to negative 15. Right? Something this might have happened, right? It decreased, the energy has decreased. So it went from did something like this, right? So what's the sign? It's negative. Does everyone understand this simple concept? Simple but important, that for an exothermic reaction, and this can go through various processes to here, I don't care what happened in between. So it went from this to this, and the energy has dropped down. Whenever energy has dropped down, that means that energy must have released. So that makes sense, that the energy dropped and the energy must have released. When you're releasing the energy, that's called an exothermic process. And this is why mathematically an exothermic process has a negative delta H. Reverse, an endothermic process will have a delta H of positive. Okay, so really understand these things, because I think these are the more important things to learn in chemistry, like these simple concepts. And I will try to confuse you in your exam on these things, so that if you really understand it, then you'll be able to score well. That's the idea. Okay, so the energy is released. Okay, so so the energy was released, but this is not any atom. This is an isolated atom. And the electron is coming out from which shell? The outermost. So sodium, which might have 11 p's here, will have 2 electrons, eight electrons, and 1 electron here. Which electron is getting pulled out? This one, because it has to come from the outermost shell. It has to be this one, okay, from the outermost. And why will I pull this outermost? Why not this electron?
Because it's most stable. It's the closest to the...
Yes, exactly. And since it is most stable, that has the least negative energy, right? So when you move out from this, the energy increases from nucleus to outward, whatever. So you have like least energy near the nucleus, and then energy increases as you move out. So this electron has more energy than these electrons, and these electrons have more energy than these electrons. Now, all these, let's assume that they are same energy, like whatever energy this electron has, the same energy this electron has. In the same shell, we call them, all these electrons are degenerate. That means all these electrons will have same energy. It's not true always, but let's assume for now that all these electrons have same energy. For magnesium, if you have done this, so the other electron might have been this. So between these two, let's assume that these two are degenerate and these two have same energy. Okay, but these two have more energy than the one inside. And since they have more energy, they are more unstable. And since they are unstable, it will be easier for me to pull out this electron, because this electron is already unstable. It's like a war zone. The most stable people are here, and these are the most unstable. So if one king is trying to breach in to the other kingdom, you won't directly go in. you would want to hit here first, because this is the most unstable one. Really away from the most stable part, which is the nucleus. Really unstable ones. So anything on periphery are more unstable. So this will be the most unstable, and that's why easier to take out. Also, you have to isolate one atom and make it gaseous. So there will be a process in which sodium solid, you have to convert it to gaseous. You don't have to think about this now, but when you're actually doing experimentations to find out, because there will be energy associated to make this sodium solid as sodium gas. There might be things that are already gas, right? Like fluorine. So this already is fluorine, chlorine, oxygen. These are already gas. O minus plus an electron. To make this a plane field, we convert everything into a gas and then compare the ionizations, not from this solid, because this is also an exothermic process, because you need energy to convert a sodium solid to a sodium gas, right? So if you break it down, its energy required is an endothermic process. You're removing an electron, and you're removing an electron from the outermost shell from an isolated gaseous atom. And the energy required to remove that is called ionization energy, or IE. Okay? Now, what do you think? Now you understood the definition, right? There's no problem with the definition. Now, once you have understood the definition, think about it and tell me which is going to take more energy. Which of this process is going to take more energy? Also, think about, compare Na with K. Compare these two and compare these two. Basically, I'm asking you which among these have higher ionization enthalpy? That's my question. But since we understood the process, let's see it in a way of a reaction and try to find out which takes more energy.
It would be magnesium.
Correct. That's
Would the potassium and sodium be the same?
yeah. Between these two, who is going to take more energy? Always draw the the structure and see.
Sodium has more protons, so would it take more?
Does sodium have more protons?
Not sodium, no, potassium.
So which has more ionization, sodium or potassium?
Sodium.
Okay, Venus says sodium. Brian? Potassium. So potassium will take more energy for an electron to be pulled out.
Yeah.
Why?
Because it has more protons, more charge holding it there.
Okay, but it also has more orbits.
Yeah.
Did you consider that?
No, that's why I was thinking it would be pretty close, because they would both only have one.
So, okay.
That was my reasoning for sodium, is that it had less orbits. So
Let's compare the sizes.
because you're looking at the last electron, and the last electron's further from the.
And since they each only have one electron in that outer shell.
Right, but let's go to the sizes then quickly. What's the size of sodium? It was
3. Oh.
no, we got 1.9, right? And potassium?
1.5. I can't remember.
2.35 angstroms.
2.35. Okay. Which electron will be easier to pull out between potassium and sodium? Easier to pull out.
Potassium.
Potassium.
Is farther away.
Farther away.
Larger order.
It's larger. Larger, easier to pull out an electron, therefore less ionization energy. Easy to pull out, it's already out, so you can easily take it out, and that is why,
You asked which had more, right?
whatever, like if you get it, so the thing is, the ionization enthalpy of potassium is less than sodium, and the ionization enthalpy of magnesium is more. And why is that? Think about the size.
So ionization enthalpy increases from left to right.
And what happens? Decreases. And why?
Because the vein is getting smaller.
It's getting smaller.
So now let's go along the period. So along the period, the sizes are getting smaller and smaller. So they're getting closer and closer. So when you're getting closer to the base, to the nucleus, it is getting more difficult for me to take out the electron. And that is why the ionization enthalpy increases, because you need more energy to pull that electron out. So ionization enthalpy should increase from left to right. Make sense? Ionization enthalpy should decrease from top to bottom in a group, because the sizes now are becoming larger as you go out, and it is becoming more and more easier for you to pull out the electrons, because that's what ionization enthalpy is. Right? Now, what is this? It's a cation. Right? And metals form cations generally. So, my question is, based on your understanding of ionization enthalpy, the tendency to form cations, what's happening to that from left to right?
Decreasing.
Decreasing? Okay. Is everyone on board? Tiffany? Is it making sense? I know this is a lot of discussion for a very small thing, but once you understand this small thing, things will become much more clearer when we discuss about geochemical classifications of elements, cosmic chemical classifications, and what things are. So you must have heard about siderophile, lithophile, stuff like that. It will become much more easier to understand once we understand these processes.
I think you're effectively rewording what is ionization enthalpy when you ask what is the tendency to form a cation.
Yeah.
Because you're just asking what is the tendency
Yes.
of an atom to lose
Yeah.
an electron.
Yeah.
So if the tendency for ionization enthalpy is to increase from left to right, then the tendency for a cation, i.e. an atom to lose an electron, is also that same trend.
Think about this.
Or it would decrease.
It's the opposite.
The opposite, sorry.
Right? Because if the ionization energy is increasing from left to right, things will be easier to pull out electrons here than here. So things will be easily going to cationic state this side rather than this side. And things that go easily become cations have a more metallic nature than the things that do not form. So, if ionization enthalpy increases from left to right, the tendency to form cations decrease from left to right, and the metallic nature also decreases, because what is metallic nature? The tendency to form cations. Like that's what we have agreed, right? Now for the group, ionization enthalpy is decreasing, so the metallic nature is increasing. So where in the periodic table, so let's metallic nature decreases, increases. So where will you find the most metallic element? Which part?
Row 1 at the bottom.
Yes, left and bottom.
Or column 1.
Yeah, column 1. So that means which group has the most metals? 1A, and that is why the metallic natures, and you can see it beautifully in the periodic table. So all the metals are on the left side because the metallicity is decreasing. Things are becoming less and less metallic. And things are becoming more and more metallic when you go down. See, carbon, like group 1, group 2, all these are metals. So cesium, which sits left, right? Francium is just very radioactive, so it's very difficult. This is the element with the most metallic nature, cesium. And which is the least metallic? Where would you have to go? Right and up. Like leave the gases which are all inert, they are not forming anything, but they are still non-metallic because they are gases. You don't find any metal gases. These are all 18 groups are all non-metals essentially, right? So you have all the non-metals towards this side. For example, carbon, silicon, germanium, tin, lead. See, this is group 14. This is a non-metal, metalloid, metals. So you can see this trend. In group 1A, everything was metal, right? So like lithium, sodium, potassium, rubidium, cesium, all these are metals. So that trend of increasing metallicity is not very obvious unless you go into the numbers. But in here, it's very obvious. Carbon is a non-metal. Silicon is a metalloid, right? It's not a non-metal, not a metal. Germanium, what's the special thing about germanium? Which is the liquid metal? What are the liquid metals? Mercury is one. Is germanium or it's gallium?
Gallium.
Gallium is like the liquid in the melts in your hand, right? So it's here. So that the same trend is also you can see in group 13. Nitrogen, phosphorus, gallium, antimony, something like this. But the trend is more like clear here. So this is definitely like not a metal. These all are metals. Lead is definitely a metal, right? So you can see the metallic trend increasing from top to bottom. The reverse is also true. Now we can look into the reverse. Like if the metallic trend is increasing, the non-metallic trend just has the opposite trend, right? It's just very simple. Now, metal oxides behave as bases. What's a base? So all these things are really connected with just one thing. And I'll bring in two other things, two other properties, and that will really sum it up for most properties. What was I going to say?
What's a base?
What's a base? Sorry. I just saw that and I just started thinking and I forgot. Base. You must have heard about these terms.